One of the methods to find the roots of this equation is to make use of the De Moivre's theorem. And to do that, I'm going to re-express what I have on the right-hand side into its Euler form. If I were to observe this on an Argand diagram, it is going to look something like this, which means that the modulus is 8 and the argument is minus pi over 2, which means that this can be re-expressed as 8 e to the power of minus I pi over 2. So if I were to apply the De Moivre's theorem, z is going to be 8 to the power of 1 over 2 e to the power of I of minus pi over 2 plus 2k pi divided by 2, where k is just any two consecutive integers. I'm going to go for 0 and 1. So for the first root, it is going to be when k is equal to 0. I'm going to call it z1. It is equal to 8 to the power of half. It is square root of 8 e to the power of minus I, substituting 0 into here, minus I pi over 4. Since we are supposed to re-express the roots in its Cartesian form, I'm going to rewrite this as square root of 8 of cosine pi over 4 minus I sine pi over 4. 8 is 2 square root of 2, and this is 1 over square root of 2 minus I 1 over square root of 2. So if I were to multiply in, it is 2 minus 2i, and that is my first root, z1. My second root, it is when k is equal to 1, and I'm going to call it z2. z2 is going to be square root of 8 e to the power of, substituting 1 into here, it is going to be e to the power of 3 pi over I 3 pi over 4. And again, I'm going to re-express it in its Cartesian form. So it is square root of 8 cosine of 3 pi over 4 plus I sine of 3 pi over 4. 8 is 2 square root of 2. Cosine 3 pi over 4 is minus 1 over square root of 2. Sine 3 pi over 4 is 1 over square root of 2. So z2 is going to be equal to minus 2 plus 2i.